Hi AP Stats, and welcome to Chapter 2, Modeling Distributions of Data. Today we're going to take a look at Section 2.1, Part A. And the purpose of this video is to help summarize the notes. So the strategy should be that you watch and listen, and then pause and go back and fill in. When you come to a check understanding, you should pause the video, try the check understanding, and see how you did. Okay, so our first learning target today is to find and interpret the percentile of an individual value in a distribution of data. Now, in previous math courses, you may have talked about a percentile being the percent of values below a given data value, which is commonly how percentile is understood. The AP exam now will be taking a look at percentile as the percent of values that are less than or equal to a given value. So even though most of the time we think a percentile is the percent of the values below a given value, for this class we are going to take a look at it as the percent of values that are less than or equal to a given value. So if you take a look at the example below with the stem plot, it represents the number of wins for 30 Major League Baseball teams in 2009. And they ask you to find the percentile for the Colorado Rockies, who won 92 games. Okay. So when we take a look at the Rockies, we have 25 teams that are at or below it. So what I went ahead and did is I looked at each leaf in the stem plot, and I tallied the frequency at the end just to make it easier to add up. So the Rockies were at 92 games. We see that if we count them all up, there were 25 teams that were at or below 92. So it's 25 out of 30, which is the 83rd percentile. The New York Yankees have 30 teams at or below it. So that puts us at 30 out of 30, which means that the New York Yankees would be at the 100th percentile. Now, we notice that the Royals and the Indians both have 65 wins. So if we go ahead and take a look at them, since they both have 65 wins, we're looking at the values that are at or below 65. We have a total of 5 values that are at or below 65, so they are going to be at the 17th percentile. Now, as we take a look at learning target number 2, we're going to estimate percentiles and individual values using a cumulative frequency graph. So we'll take a look at what we have below here. And I'm giving you this problem. What you're going to learn is these are ages of presidents at the time of inauguration, and this is the frequency of the ages within each category. So I can take the frequency and I can go ahead and calculate the relative frequency, which is the percentage of each age and each of the amount of ages for each category. Now, what the cumulative frequency does is that's going to allow us to find the percentiles. So from age 40 to 44, we take a look, we have 2. Now, cumulative frequency says, what's it going to be from 40 to 49? Well, that'll be 2 plus 7. That puts us at 9. From 40 to 54, if we add all of them up, it's going to be 22. From 40 to 59, we're going to add 12 to the 22, putting us at 34. And as we continue through, if we go all the way from ages 40 to 69, that would be all of the frequencies put together, which would give us 44. Now, we can go ahead and calculate the cumulative relative frequency. And from the cumulative relative frequency, it's going to allow us to calculate percentiles. So if we take a look here, we have 2 out of 44, which is 4.5%. For the second group, from 40 to 49 was 9 out of 44, 20.5%, all the way up to where we got to 44 out of 44, which was 100%. We will use these cumulative relative frequencies to graph our percentiles. Okay, so let's take a look at this cumulative relative frequency graph. You'll take a look here, and our cumulative relative frequency graph, you'll notice that the y-axis will have the percentages. This case, it was written in terms of the actual percent, but also the graph could be written in terms of 0 to 1. So just pay attention to how the graph is being drawn. So as we look at this, you'll see that I have kind of gone through and lightly outlined the bar graph of all of our relative frequencies. So ages 40 to 45, we had 2 out of 44 was 4.5%. So you can see how I have kind of lightly drawn that in and did that for each of the categories, where the final one ended up all the way up to 100%. Now, to make this graph, you plot a point corresponding to the cumulative relative frequency in each class at the smallest value of the next class. For example, from 40 to 44 class, we plot a point at a height of 4.5% of the age of 45. Okay? This means that 4.5% of the presidents were inaugurated before they were 45 years old. So we can see how this falls into in relationship with our percentiles. We'll be using this graph to help us answer questions about different percentiles. Okay, so let's use our cumulative relative frequency graph to answer the questions below. Was Barack Obama, who was inaugurated at age 47, unusually young? So we go over to our graph and we find where age 47 would be, and we draw a line up to see where it's actually going to hit the line in our graph. So we find where it hits and we go over to our y-axis to see where that matches up. It's somewhere about almost halfway between 0 and 20. So it's approximately close to 10. So we're going to say Barack Obama's age was around the 10th percentile. So yes, he was unusually young. His age is around a 10th percentile. About 10% of the U.S. presidents were Obama's age or younger when inaugurated. Now we want to go ahead and interpret the 65th percentile of the distribution. This time we're going to take a look at the y-axis and we're going to see where the 65th percentile would fall. So we find it and we go over and draw a horizontal line to see where it hits our graph. And then we drop down to see what age that would match up with. And we see it's a little bit below 60, so somewhere around 57. So the 65th percentile is around the age of 57. 65% of presidents were 57 years old or younger at the time of inauguration. So now pause the video and take a few minutes to try the check understanding questions. Okay, so for the first multiple choice question, the correct answer is C. Mark did better than about 68% of the students who took the test. If his score placed him at the 68th percentile, it means about 68% of the students are at or below his score, so he did better than about 68% of the students. For question number 2, Mrs. Munson is concerned about how her daughter's height and weight compare with those other girls of the same age. She uses an online calculator, determined that her daughter is at the 87th percentile for weight and 67th percentile for height. Explain to Mrs. Munson what this means. So she's at the 87th percentile for weight. 87% of the girls of the same age have a weight that's less than or equal to her daughter's weight. If she's at the 67th percentile for height, 67% of the girls of the same age have the height that is less than or equal to her daughter's height. Now, for questions 3 and 4, you were taking a look at the relative cumulative frequency graph, which represents our percentiles, that's over here on our y-axis, for the length of calls in minutes. So about what percent of calls lasted less than 30 minutes? So we find where 30 is and we go up and see that as we draw it across, it's just above 60. So we are going to see that about 65% of the calls are less than or equal to 30 minutes. Remember, when we are interpreting the percentile, we are going to say that it's less than or equal to that value. So that means if 65% are less than or equal to 30 minutes, about 35% of the calls are going to be more than 30 minutes. Now, to find the Q1 and Q3 of the distribution, we have to remember that Q1 is equivalent to the 25th percentile and Q3 is equivalent to the 75th percentile. So to find this 25th percentile, we go over to our y-axis and find 25%, and we see where that lines up on our graph, and it's going to fall at approximately 13. To find Q3, the 75th percentile, as we line that up on our graph and we draw it across, we see that that's going to drop down somewhere between 30 and 35. I estimated it to be about 33. So Q1 is at 13 minutes approximately, and Q3 is at 33. So therefore, the interquartile range will be at 19 minutes. Okay, our third learning target is to find and interpret the standardized score, which is the z-score of an individual value in a distribution of data. So another way of measuring position is to determine how many standard deviations above or below the mean an individual data point is. This is called computing the z-score. This process is also known as standardizing. So anytime you hear standardizing or find the standardized value, you have to know that they're also saying find the z-score. So standardized value and z-score are interchangeable. If an observation from a distribution that has a known mean and standard deviation, has a known mean and a standard deviation, a z-score or standardized value of x can be calculated by finding the value minus the mean and dividing by the standard deviation. This will tell us how many standard deviations the given data point is from the mean. So again, when interpreting it, it's always important to put context back in. So as we take a look at the problems below, they just go ahead and they ask you to find the standardized scores. So again, if they're asking to find a standardized score, you're finding the z-score. So the Red Sox had 95 wins. So to find the standardized score, we go ahead and plug it into the formula, and we come out with the value of 1.22. So this tells us that the 95 wins is 1.22 standard deviations above the mean. When we calculate the Braves, we come out with 0.44. And then we also see that the Nationals, who have 59 wins, comes out with a z-score of negative 1.92. If the z-score or standardized score is negative, it means it's going to be below the mean. And we can see that the Braves were actually closest to the mean because their z-score was the smallest. Okay, so take a couple of minutes, pause the video, and try to check your understanding. So for the first question for the check your understanding, Lynette is 65 inches tall. When we calculate the z-score, we come out with a value of negative 0.47. We interpret that as Lynette's height is 0.47 standard deviations below the mean. Brent is 74 inches tall. When we compute his z-score, we come out with 1.63. Brent's height is 1.63 standard deviations above the mean. For the last question, we know the mean height of the players on a team is 76. We know that Brent's height has a z-score of negative 0.85. And the question asks us to find the standard deviation of the team members' heights. We know the formula for standard deviation, so we're going to take the information that we have and plug it in. So negative 0.85 equals 74 minus 76 over the standard deviation. As we simplify that, we can continue to solve for our standard deviation following our solving steps, and we end up with a standard deviation of 2.35. So now that these notes are done, it is your job to continue through, and I would like you on the last page to go through and summarize the 3 learning targets for this lesson. By summarizing these, it's going to help you solidify what you are supposed to understand from this topic, from the lessons from today. Thanks AP Stats, and have a great day.